5G and artificial intelligence are two of the most formative technologies of recent times. Both are expected to deliver seismic shifts in the markets, value chains, and even market dynamics. In both subtle and obvious ways, we are seeing impacts of both 5G and AI infused within our consciousness today. For those of you who are new to 5G, conceptually, 5G embodies the personas of Wi-Fi and wires. On one hand, it possesses all the conveniences of being wireless, which we all love. On the other hand, it possesses the speed and reliability of wires. Among these unique properties and many more, many foresee 5G as the next major technological wave. Today, you are already seeing 5G enabled in next generation smartphones, telecommunication infrastructure like cell towers, factory robotics, remote healthcare, and many other novel applications. Now let's take a look at artificial intelligence as another major pivotal technology. AI provides unprecedented intelligence to machines via training, heuristics, and inference. Having machines that think extends the principles of automation to a new dimension of efficiency and reliability. One can quickly envision a new world of collaborative robots, autonomous driving, and computer vision, just to name a few. For example, think of a fully autonomous car needing to apply brakes all by itself in a matter of milliseconds. Or think of a robot on a factory floor with micrometers of precision driven by artificial intelligence. Traditionally, communications, which is 5G, and compute, which is AI, are treated as two mutually exclusive topics at implementation level. One of the greatest joys as designers and architects is to work on both sides of creative intersections. We like to think that at application level, these two technologies, 5G and AI, can complement each other. For example, there can be AI enabled by 5G and also 5G enabled by AI. The aha moment came to us when we realized that these two fields are not mutually exclusive. When it comes to basic operations and hardware requirements, there are major synergies. For those of you who are new to 5G and wireless, there are some basic functions in wireless communication, like time to frequency and frequency to time conversion, popularly known as FFTs and inverse FFTs, modulation, demodulation, channel estimation, equalization, and MIMO detection, just to name a few. It turns out that the mathematics for a lot of these functions is comprised of following operations. For example, dot product multiplication is employed for FFT and channel estimation. Equalization and MIMO and user detection employs max and average of a vector, and so on. Now let us look at some basic functions of AI. They are convolution, pooling, average and max, nonlinear functions, normalization, just to name a few. It turns out, mathematics behind a lot of these functions is also comprised of a very similar mathematical operations, which we came across in 5G. It looks like, from an implementation perspective, these two fields are not mutually exclusive. Interestingly enough, if you look at the literature, a lot of concepts of machine learning originated from information theory itself. Let us test our hypothesis by taking a closer look at some of these operations. Very common in 5G and communications in general is a very basic mathematical operation of dot product multiplication. Dot product multiplication is required to compute fast Fourier transform, channel estimation, and many other operations in communications. This operation is typically done over 16-bit complex numbers. In a very parallel universe, the most commonly used mathematical operation in AI inference is convolution, where a weight matrix slides over the data matrix and does dot product multiplication. These are typically 8-bit, 16-bit, or 32-bit real numbers. You will immediately notice that the multiplier operation is common. It is just that the data is fed to the multipliers differently. Let us now look at another mathematical operation. In communications, channel estimation is done to extract useful information from the ingress data. As shown, a transmitter inserts several pilot tones in the transmitted data. At the receiver end, these pilot tones within the estimation window are fed to an averaging hardware to estimate the channel. Weighted average or normal averaging is then used depending on the type of channel. So what is the mathematical corollary in AI? Average pooling is a very common operation in the field of AI to reduce data size and to provide invariance to rotation, translation, and downsampling. For those of you who are new to AI, the AI engine should be able to identify a cat irrespective of its orientation. An upside-down cat is still a cat. Averaging provides invariance to this rotation. Notice how the same hardware is utilized to compute averaging of a given dataset. Let us look at another pooling example as it relates to 5G. This is finding the maximum or a peak. To enable a call, the user must establish a handshake with the nearest base station. Determining the peak of an incoming data is typically employed in communication to identify the users and their timing. Notice that the waveforms of different users are being fed to the max pooling hardware. Once the peak occurs, the presence of a user and its timing is identified. The user is now allowed to link to the base station. Another direct application in telco, specifically Open RAN, is during EC pre-compression and decompression. Max estimation is used to find maximum tone and therefore bit occupancy corresponding to that tone. Communication systems field is full of many such examples. In the field of AI, max pooling is typically used to reduce the data size while keeping the translation invariance. Now let us look at how the same max pooling hardware is employed in the context of artificial intelligence. Just to recontextualize, while 5G and AI are often treated as two distinct topics, both utilize the same computational hardware and mathematical operations. The same hardware for dot product multiplication and convolution, as well as average and max pooling, are not only analogous but can be harnessed by both the fields. Another fundamental commonality between 5G and AI inference acceleration is their unforgiving mission-critical nature. Every microsecond of latency and time sensitivity matters. In some cases, the difference between life and death, profitability or loss. And therefore, both rely on locality of memory. For example, in 5G, receiving a phone call requires data to be processed within a fraction of a millisecond. Applications requiring URLLC, ultra-reliable low-latency communication, need to access memory even faster. In both fields, time to access the memory is crucial. Neither can afford to store or access memory off-chip. By no surprise, when we analyze both 5G and AI, the on-chip memory requirements are the same. Now that you understand memory locality, let us apply this principle to examples of memory-bound operation. As discussed before, in the 5G physical layer, FFT is a very time-critical operation. A typical FFT over 4K data takes only a few hundred nanoseconds, which makes on-chip memory imperative. Similarly, hybrid ARQ process requires on-chip memory. For AI inferencing, such as level 4 driving, inferencing decisions need to be made in a matter of milliseconds. For data center AI, a few millisecond delay in inferencing can cost billions of dollars in revenue. Lastly, a very common mathematical operation employed in 5G and AI is the use of nonlinear functions. In 5G, 1 over x is used to compute signal-to-noise ratio and also to normalize the input data. The square root of x is used to find magnitude of a complex number. You might remember Euler's formula, which is used to represent a complex number as sine and cosine. In communication, rotation of this phasor is of interest, and we use arctan operation to compute the rotation. Now let us look at some most commonly used nonlinear activation functions in the field of AI. For the starters, in AI, neural networks are great universal function approximators. To be able to apply any function, we need nonlinearity. That's where the activation functions come into play. They are used to add nonlinearity to neural networks. Without activation functions, neural network can be considered just as a collection of linear models. Few of these activation functions are tanh hyperbolic, swish, sigmoid, softmax, ReLU, and others. The same basic hardware which creates nonlinear functions for the communication can be employed to create nonlinear activations for AI applications. For the math enthusiasts out there, for both 5G and AI, we do not create dedicated hardware for each of these functions. The way these are created is by doing piecewise nonlinear approximations on a second-order polynomial based on Taylor series expansion. So once this approximation is created, any nonlinear function can be realized using the same hardware. As academics, we are drawn to synthesizing correlations unseen by most. And as technologists, we are drawn to derive new forms that are unstated. The art in all of this is in the design. Our discovery is that 5G is a natural superset of AI. where 5G requires extra processing elements like FEC decoders, encoders, beamforming, and packet processing, etc. An AI inference accelerator requires more emphasis on memory locality and host software. If properly architected, there is now a world of applications in which AI enables 5G and a world where 5G enables AI, all collapsed in a transparent manner for enterprise, telco, and the edge. Until next time.